Hey guys, so this will be the beginning of section 1 for chapter 4. As I mentioned in class, section 1's pretty long, so I kind of wanted to get this video to kind of front load you on some of the information so when we got in class we could work through some of the examples together. Chapter 4 is a pretty long chapter. It's going to span over everything we do up until Christmas. It's all about quadratics. The beginning talks about graphing quadratics, then we will look at solving quadratics by several different methods, and then we'll put it together with some applications towards the end. So the first thing, now, please keep in mind as we start this, we have seen some interaction with quadratics as we've gone along so far this year, so this shouldn't be all foreign to us. Okay, so standard form of a quadratic equation. If I'm going to write a quadratic in standard form, it looks like this. It looks like ax squared plus bx plus c, where a, b, and c are numbers. Now, we've dealt with quadratics before, but when we looked at them before, they were in a different form. We saw quadratics in chapter 2 when we did transformations, and we used a different form for them then. Okay, I hope you know the next one. When you see quadratics on a graph, they create that U-shaped curve that is called a parabola. Again, we should have some familiarity here because we did graph these in our transformation unit. Okay, parabolas, they fall in one of two categories. They can either open facing up or open facing down. Parabolas will never open left or right because then they wouldn't be a function anymore. So you could, in your graphing calculator, create a sketch for these two graphs. So I could open my calculator up. You could go, so when you open, you're probably on a blank screen. Go to y equals. Make sure you don't have any scatter plots turned on. And you could enter the equation. So look at the one on the left first. You could type in x squared plus 2x minus 5. And go ahead and graph that. You get your parabola, your U shape, facing up. If you want to sketch that one in, that looks something like this, give or take. Okay, similarly, we could look at that second equation. If I go back to y equals, and I type that one in instead, this one is negative x squared plus 3x plus 7. Grab a quick sketch of that. That one is my U-shaped parabola, but this time it's facing down. So looking something like this. Pretend that's a better U. Now, I think that you should have known that based on what we did with quadratics in chapter 2. I think that you should have been able to look at that equation, maybe not know its exact location on the graph, but you should at least have known if it was open up or open down. And hopefully you remember that comes from that lead coefficient, or as we're talking in standard form, our a value. So if our a value is positive, like the one on the left, the parabola opens up like a smiley face. If our a value is negative, like the equation on the right, then our parabola opens down. And again, I hope that's familiar to you from what we did back in chapter 2. Now, the other thing that parabolas have that I think we talked about, but it's worth mentioning again, parabolas have what's called an axis of symmetry. You have an axis of symmetry straight down the middle of you, just like parabolas do. An axis of symmetry is an imaginary line that's going to cut our parabola into two equal parts. So our axis of symmetry is an imaginary, whoop, I should spell. Line that divides the parabola into two equal parts, meaning that they match up, so to speak, on both sides. Now, even though I think we mentioned this earlier, we did not find the formula for the axis of symmetry. So let's talk about that briefly. When I talk about axis of symmetry, it does have a formula. Its formula looks like this. It's a line, and it happens to be a vertical line. So it's an x equals line, and it is opposite of b over 2 times a. So when that equation is in standard form, it's the opposite of the b value over 2 times a. Now, another key component of a quadratic when we're graphing it is its vertex. We looked at the vertex a lot. I don't know if I often referred to it as the vertex in chapter 2, but when we had transformations and we moved left, right, up, down, and we dotted a point, that was the vertex point. So when the vertex point happens to be the lowest point on the graph, it is called a minimum value. That occurs if the parabola is facing up. So then the vertex is actually the smallest point, right there in the center there, the smallest on that whole graph. If the vertex is the highest point, it is called a maximum value. And that actually takes place if the parabola is going upside down. And that vertex is right there in the center. Okay? Now these first couple examples, what I want us to look at is I'm going to give you an equation. I want you to find its axis of symmetry, the equation of that line, the coordinates of the vertex, and the opening direction. In my opinion, it's probably easiest to jump to the opening direction. So I think that's something that you can just look at and tell. So if we look at number 1, it is in standard form. It says y equals x squared plus 8x plus 15. I'm hoping that you can look at that and know, since that a value is positive, this opens facing up. Now, when we talk about axis of symmetry, as I mentioned, axis of symmetry is a line. It's an imaginary vertical line down the middle of the parabola. It has an equation. Just to refresh, our equation looks like x equals opposite of b over 2 times a. So in this particular problem, my b value is 8. So opposite of 8 would be negative 8 over 2 times our a value. And in this case, our a value is 1. When I'm simplifying this, make sure you simplify the denominator first. So 2 times 1 is really 2. So I have negative 8 over 2. Or the axis of symmetry is at x equals negative 4. So it's a vertical line that runs through negative 4. Okay, now when I switch gears and find the coordinates of the vertex is an ordered pair. When we did this in terms of transformations, we were moving left, right, up, and down to find the vertex. But this equation in standard form is not a form that I can easily move that left, right, up, and down. When we did that, we were in a different form. So later we'll talk about how we transform the equation from standard form to that other form. But right now we're going to work with what we have. So the coordinates of the vertex is an x and a y value. The x value is always the same thing as whatever the axis of symmetry is. So my x value is negative 4. Now to find the y value, I'm going to utilize the fact that I have an equation. So I'm going to go to my equation, I'm going to plug in negative 4 for any and all x's to find my y. So I know that y equals x squared, or negative 4 squared, plus 8 times negative 4, plus 15. And at that point, to find the y value, you can either plug that in the calculator, you can do it by hand, whatever easiest for you, but one way or another, the y value should be negative 1. So your vertex is at negative 4, negative 1. Okay, so flip on the back for a second. 2 more examples of the same thing. So I'm going to go through number 2 with you, then I'm going to ask you to pause it and try number 3. Okay, similar idea in that you have an equation in standard form, y equals negative x squared plus 10x minus 23. The first thing I think that you should be able to do is determine the opening direction. So, looking at this parabola, this equation tells me that we open up because it leads, my fault. It opens down because it leads with a negative. Okay? Now if I want to find the axis of symmetry, remember, it's an equation. That equation stays the same at all times. It is x equals opposite of b over 2 times a. So in this case, our opposite of b is 10, so we have negative 10 over 2 times negative 1. As I mentioned before, remember to clean up the denominator first. So 2 times negative 1 is negative 2. So my axis of symmetry is that x equals positive 5. Now my vertex is just an ordered pair, or it's just a coordinate. So I need an x and a y. The x value is always whatever I got for the axis of symmetry. And to find the y, I'm going to have to plug it in. So I'm going to have to say negative 5 squared plus 10 times 5 minus 23. Again, if you want to plug it in your calculator at this point, great. If you want to do it by hand, that's fine too. One way or another, you should get that y is 2. So the coordinates for the vertex here are at 5, 2. So take a second, pause the video, and try number 3. All right, let's see how we did. So right away, you should have known that it opened up. It led with a positive. The axis of symmetry, this one was maybe a little tricky, the negative b over 2a, or opposite of b over 2a is normally what I like to say. If b is already negative, if you're saying the opposite of negative 12, that makes it a positive 12. So make sure you're aware of that, that makes it a positive 12. So the axis of symmetry was at x equals 2. Coordinates of my vertex were at 2. Plug it in, and I get negative 7. Now, what we're really utilizing all this stuff for is to be able to construct a graph. And not just a graph like we did when we were doing transformations, but a complete graph. So in order to graph this, I need to find the axis of symmetry, which we know how to do, find the vertex, which we know how to do. This y-intercept and mirror image point, that's new for us. We haven't talked about that yet. And then domain and range, that is a good review for us from stuff we've done earlier in the year. So let's go through this one example at the bottom, and then the video will stop and we'll pick up with everything else in class tomorrow. All right, so looking at this quadratic, it says y equals x squared plus 2x plus 5. Again, in subsequent stuff, I'll probably move opening graph up to the top because I like to answer that question first. I know that this graph opens up because it leads positive. Now, when I'm looking for the axis of symmetry, forever and always, that formula looks like opposite of b over 2a. So in this case, b is positive 2, so I have the opposite of that is negative 2 over 2 times 1. Clean up my denominator, 2 times 1 is 2, so I have negative 2 divided by 2. The axis of symmetry is at x equals negative 1. Now, since I'm actually going to use this graph, I want to put that in there. So I want to construct that if the axis of symmetry is at x equals negative 1. That's an imaginary line. So I'm going to kind of show that just at a dotted line of x equals negative 1. Okay, in terms of my vertex is an ordered pair. I know it's going to start out with negative 1, but it's got to be negative 1 something. So I'm going to go to the equation. I'm going to work up here, so I'm running out of room, and plug everything in. So I have negative 1 squared plus 2 times negative 1 plus 5. And again, I don't care if you use your calculator. I don't care if you want to work this out by hand, but one way or another, you need to come up with the fact that this ends up being what your y value should be 4. So my vertex is at negative 1, 4. So I'm going to show that on my graph. So negative 1, 4 is right about here. Okay. Now my y-intercept, we haven't talked about this yet. The y-intercept for a quadratic is very similar to the y-intercept for a linear in the sense that it's the c value, or the constant that's by itself. So this y-intercept is at, the c value is the value by itself is at 5. So the y-intercept is at 0, 5. Because all y-intercepts have an x value of 0. So I'm going to graph that. 0, 5 is right here. Now, this is where I'm going to utilize the point, or the idea that we have an axis of symmetry, because that means I have a mirror image point. So 0, 5 is on the right of my axis of symmetry. If I think about literally reflecting that point, or flipping it over on the other side of the axis of symmetry, I would find myself right here at negative 2, 5. Okay, so my additional point on the graph is at negative 2, 5. And again, I got that by utilizing the point of the mirror image with the axis of symmetry. So once I have 3 points, that's kind of enough to sketch in this parabola, this U shape. There's my graph. And the last question I have here is about domain and range. Now, domain and range are things that we've talked about before. Remember, the domain is my set of x's, the range are my y's. So in this case, my domain is negative infinity to infinity, and my range is at 4 to infinity. So like I said, keep this, and we'll pick up with the extra examples tomorrow in class. Thanks, guys.